Go ahead.
Okay, so welcome to today's seminar in Chile. We have the pleasure today to have Timo Vilkas from Lund. And I should say that for those of you that are interested with high probability, if I may say, Timo will visit Chile in January, and hopefully he'll give also some course on some topic of interest for some of the students that are here and also for us, for the researchers. So I'm very much looking forward to his talk now on Make a Breaker games on Galton-Watson trees. So please, Timo.
Thank you, Dieter. Yeah, I can say that the probability, if not another pandemic comes, should be very close to one. Because I was supposed to come to Chile in 2020, and then you know what happened in 2020, so that never took off. But hopefully, it will not be in the way this time, some bigger pandemic. Cool.
Okay,
I'm really
please.
happy for the invitation. I first thought to be funny, I put my pajamas, but then I thought it's maybe not so appropriate. So I despite the daytime here, I dress appropriately. I hope so, at least. I'm going to talk about some work of mine which deals with make or breaker games. I will define that in case you haven't heard it before. And the random board it is played on will be Galton-Watson trees. So it's a game that is played on a graph, and the graph will be random here. But in case I name anything that you haven't seen before or find sort of that it needs more explanation, please stop me and just raise a hand or like even better, speak up. All right, so the talk will have three parts. The first part, I will introduce the two concepts in question here, the make or breaker game and the Galton-Watson trees. I expect you to know the latter better than the former, but as I said, I will shortly go through both. And then we were going to look at different let's say different variants of the game, because it will turn out that it depends how the game is going and who will win it, not only on different things like who starts the game and what kind of distribution we have to generate the family tree, the Galton-Watson tree, but also how far down the tree the players are allowed to look, like how much information they get, how the tree looks like. And this is now only like a cryptic notation here, but it will make sense soon, I hope. And then the last and a bit shorter part, maybe I want to sort of point out some observations in case you missed them and some open problems, because there's still a lot of work that could be done. So let me start with the game itself. Make or Breaker, as I said, is a game that you play on a graph and your moves are basically the edges. So the idea works like this. You have all the edges as potentially there or not there, almost like in percolation, but you don't flip coins, but you rather take turns. So one player is called Maker, and the other player is called Breaker. And pretty much as the name is telling it, Maker can sort of glue an edge or fixate the edge or hammer it down or whatever it does so that this edge is there forever. And if Breaker gets hold of an edge that is not already fixated by Maker, he removes it. So they're taking their turns and either gluing an edge so that it's there forever and safe from removal, or Breaker by removing the edge. And every edge obviously can only be played once, because once it's gone, it's gone. And once it's fixated, Breaker cannot destroy it anymore. What's the aim of the game? There are a bit different variants. In my case here, we look at the very simple one where the game is basically to isolate the origin. So one vertex in the graph is sort of marked as a vertex to protect or to look at, especially, so to say. And then Breaker would try to cut it off from the rest of the graph, and Maker tries to prevent that. As I said, there are different games where, for example, Maker tries to build a matching and Breaker tries to prevent that, or there are plenty other games that are not necessarily this connectivity game here. But we're not going to go into those, just in case you saw some related work. I will, in general, assume that Breaker starts the game, but we'll also name on the side how the probability for win of one or the other changes if Maker starts the game. So that's just who is first, whose turn is first. Can Breaker first remove an edge, or does Maker start by gluing an edge? And then I want you to understand that this 1-1 game, so 1-1 stands for how many edges, because there are also biased versions of the game where, for example, breaker starts by removing 5 edges, and then maker can glue 2 edges, and then breaker again gets to remove 5 edges, and so on. So that would be the 5-2 game. But we're going to look at the most simple one where they go 1 edge at a time. That's the 1-1 here. And I want to point out that it is deterministic, because as soon as the graph is given, so if not, it's a random graph, sure, then it's random who wins and who doesn't win. But if I give you the graph fix as either a realization of my random graph or as a deterministic graph, then the game is completely done, because they're playing optimally. So they will always move, like take the next edge according to what is best for their agenda. So there is no randomness once the graph is fixed. There's no randomness in their strategy. And that's what I try to point out here. So even if the graph is unknown, they are going to play optimally in the sense that they try to keep their winning probability as high as possible, both of them. So essentially, as you will see in the different regimes, they basically aim for the same edges. And it's especially simple when you look at the tree, but we're not right there yet. We'll get there. And just one small piece of notation, I will write P for the probability that breaker wins the game that she starts. And P bar is then the probability that breaker wins when maker starts. So that's sort of always the attached. So all the results are about P, but then it's not so hard to calculate actually P bar, just to keep them apart. P is when breaker starts, and P bar is the probability also that breaker wins, but when maker starts. I hope there's nothing weird on this page. It's basically in words how the game works. No, everybody seems happy. So then I will just, in case you are one of those people like myself that think that a picture can say more than 1,000 words, let's try to give you a picture of it. So let's say we have C2, the 2-dimensional grid, and one vertex here painted in blue. I worked a bit before we met here, so that's the origin. And then let's say breaker starts. So breaker, that's the eraser here, chooses to go with this edge, for example. So this edge is gone. And then maker gets a choice, and he would, for example, choose this edge. So this one is now there forever. Now it's maker's turn again, and it would choose maybe this edge. And then breaker would choose, and maker would choose maybe that edge, and so on and so on. We delete one. And then maker gets the right to choose one, and so on and so on. I don't want to bore you with that. I hope you understood what the whole thing is about. And this continues. And obviously, if maker is stupid or doesn't follow my assumption to play always optimally, at some point, maybe breaker succeeds in cutting it off completely by erasing edges so that there is no more sort of chance to, okay, I'm very crude now, no more chance to connect the origin to the rest of the grid, then this would be a win for breaker. And basically maker, it's not so easy to define the win for maker, but that's basically that this never happens. So if maker can continue claiming edges, keeping the origin connected to the whole lattice, so to say, or at least the infinite part of it, then it's a maker win. And I want to point out here something that is kind of cute, because you first might think, okay, this is a fairly easy game, but wait a second, is it really so easy to realize who wins here? Because in the 1-1 game on set 2, it's actually always a make or win. How is that easy to see? Well, you do the following, or rather maker does the following. For every vertex, you pick a pair of outgoing edges. So say this is vertex U here. You pick a pair of edges that point away from the origin. It doesn't really matter which ones. If you take, for example, the origin, you obviously have 4 outgoing edges. But it doesn't matter, you just pick a pair. So say if you're on one of the coordinate axes, this one here would have 3 outgoing edges, just choose 2 of them. So you have a subset of edges that are paired up. And how is the strategy of maker now? It's fairly simple. As soon as breaker kills one of the paired edges, this one, then maker fixates the other one. So to make sure that one of the 2 edges is always fixated. Not both of them can be gone, because when breaker removes one of them, maker fixates the other. And with this strategy, we'll see a vertex is always connected to a vertex outside of it. And by that, it's a very simple argument to run through your heads. Actually, all the vertices will stay connected. So this is even a strong win for Maker in the sense that all vertices are connected. Not only is the origin connected to infinitely many, but with the edges that are fixated and not removed yet or not played yet, but it's actually even stronger than that. So on Z2, it's a bit boring. It's a Maker win. That's why people started to look at the biased games, and then it becomes interesting again. So let's see what we want to play this game on. I hope you understood the make or breaker game that we're looking at, this 1-1 game. This will not change. This will be the rest of the talk. One of the two topics. The other one will be the classical Galton-Watson tree, and I assume most of you have seen it before. So the idea is, it was some 200 years ago that, or even more, that they looked at sort of a stochastic model for families, or rather last names, how they, we come back to that topic, how they spread in generations. And then it was only the sons, obviously, that kept the name. So it was, I don't know, one first family person with the name Smith or something had 3 sons. And then each of those sons had maybe 2 sons. This one had no kid, and this one had 1 kid, and so on. And this family tree works like this, that all the numbers of kids are IID following the same distribution Xi here in this case. So we have independent sort of procrastination, if you want, or male offspring I'm not sexist, this is just history. And I mean, nowadays, even we as a man can choose to change the name, so this doesn't work really anymore. But back then it was okay to assume we're looking only at male offspring, they keep the name, and then sort of we count in generations. So that's how the tree would look like. And obviously, I assume you have heard that before, depending what this distribution Xi is, this tree will die out at some point, or it might have a positive probability to be infinite. This is this extinction probability. This goes back to, I don't know, I think a standard reference is Atreya. It's from the 70s, this book. So you can actually calculate the probability that a tree like that dies out, or respectively that it is infinite. And this is just, if you calculate the, go back to the pointer, if you calculate the probability generating function, so Pi, that's the offspring distribution's probability mass function. So P5 is the probability that any node has 5 offspring nodes, so to say. And if you calculate the probability generating function, you immediately get the probability of extinction Q by finding the smallest root of this equation here. So basically the first time that the probability generating function intersects with the identity function. I painted here the standard picture that you might have seen before. Here to the left, we would have a subcritical, because here the intersection is, they will always intersect at 1. That's easy to check. But this is the smallest, so the extinction probability 1 means the tree dies out almost surely. And if you have a supercritical one, then you would have an intersection, and this that is not at 1, but before, and this is then the die out probability for our tree, so to say. The proof is not very hard. I'm not going to go through it. It's too standard for that, but I might go through a proof later. I hope so. I have time for that. So these are the 2 settings, and we're obviously only going to look at the right setting where it's supercritical, because if the agenda for Maker is to keep the origin not isolated in a finite component, that's obviously already lost if we start with a finite tree. So the finite, if randomness is not nice to Maker, then the start tree is already a finite tree, then it's a sure breaker win. If it's an infinite tree, the game becomes interesting, and the question then is, will Breaker succeed in cutting the branches off so that at one point of the game, the origin is connected only to finitely many other vertices? Then it's a Breaker win, and if Maker can prevent that, it's a Maker win. That was roughly what I wanted to say about the 2 elements of this basic building blocks of this talk, so to say. Are there any things that are unclear besides where is Santiago? Yes, good. Okay, then we continue. So how will the game now look on a tree in general, but on this kind of random tree in particular? So I tried to paint here another picture so you get an idea, a visual idea of the game. And you should read this in the following way. I tried to sort of draw here the internal nodes. So the ones that are connected, but you should read the edges here that are solid as already fixated by maker. The ones that are dashed, they are not played yet, so they can be either removed or fixated. And the ones that are removed, you don't see here. Plus the ones that are not necessarily visible yet. I will get to that. So I will call the vertices that are connected by fixated edges to the root and the root itself, the internal edges. Maybe I can, the internal vertices. So maybe I can just. And the ones that are connected to internal vertices with one edge that is not played yet, those are the external vertices. And both together, I will call the visible vertices. Why is that? Well, to be able to play the game, both players must at least know what kind of edges they can play with if they don't get to see the whole tree at the beginning. So what they get to see anyway is for sure the vertices that are already connected by fixated edges, but also their neighbors. So you can already understand what happens if, say, maker connects here, then this one becomes black, and we will get to see what is hanging from it. That would happen if maker plays this edge. If breaker plays this edge, well, then just this part is completely gone. So this one will be removed because that's one property of trees. If you remove an edge, you remove the whole branch. There's no way of connecting it back to the root. So in the tree, it's a bit special because with cutting one edge, you cut the whole branch. But other than that, it's the same game. And I will denote by TV the subtree hanging from a given node. That's just notation. Is that so far clear? So visible in the sense that's the information that they get at least. They will get maybe more information in different regimes. I will talk about it later. But they will always know which vertices are already connected by fixated edges plus which offspring they have.
I have a
But not
question.
more. Yes, please.
In this game, you told before that they play deterministically by maximizing their probabilities of winning, right?
Right.
However, I can see several situations in which you don't know, at least when you're not looking at the whole tree, which vertex you're going to choose. So how do you choose one?
Right. So this is actually, so I was cheating there a little bit because this is
Aha.
actually dependent, right? This is dependent on the information, but depending on the information, they play optimally. So let's just go through here. If you get no other information, we know from the model that every vertex is in principle the same, right? From it is hanging another copy of this tree. So in the situation where I don't give you any more information, all those gray nodes are just as good. There's no difference. There's complete symmetry. It doesn't matter which one you cut or which one you fixate. They're all the same. You just count the number. So we will get to that. That's maybe the easiest way of looking at it. If you have the whole tree, there's no randomness, then your problem is not even a problem. But I will look even in the intermediate where I tell you if the offspring is infinite or finite. So then we can sort of, in this picture, we get some more information. We could say we have a dark gray nodes that have an infinite offspring tree hanging from it, and light gray nodes that have a finite one. And you can already guess what happens. They will just ignore the ones that have a finite tree hanging from it because they won't help. So even in that situation, again, the ones that are interesting to play with are all symmetric. They're all the same. There is no difference.
Okay.
Actually, in this paper, there is no regime where different nodes that are interesting to both players have any difference among each other, because then it becomes really messy if you have different classes of nodes that are potentially interesting. But we'll get to that in the open problem section. But it was a very good question. So in most regimes, it will be like this. It's just a certain number of nodes that are interesting, and they are all the same, probabilistically speaking. All right? Very good.
All right.
Okay, so let's start with the first one that we shortly talked about. If I tell you with every visible node V, what is hanging from it? So we can just go back to the picture. The first node that it is visible is the origin. And if I tell you what's hanging from it, then I tell you the whole tree. So basically already from the start, the whole tree is exposed to both players and they know exactly how the tree looks like. That's what is decoded here. So I tell you with every node that you can see what subtree is hanging from it. Well, that also applies to the root. So I tell you the tree from the start. And then we have this nice little lemma here. If you play this 1-1 game on a tree T that you tell from the start, it's deterministic. And when will maker win? Well, exactly when there is a copy of the complete binary infinite tree hanging from the root. So that this is sufficient is, again, fairly easy to see, I claim. Namely, if you have this complete binary tree hanging from the root, you will just play the same pairing strategy as we talked about in set 2. So whenever maker sees breaker killing one of the kids of somebody, then it will make sure to fixate the other one. And in that sense, there will always be an infinite path hanging from the root. Right? Because to cut it off, to cut something off, you would need to cut both of those edges, but maker will not allow that. If you cut one of them, it fixates the other one. So in this strategy, in this pairing strategy, you make sure that if there is a complete binary tree, infinite binary tree hanging from the root, ignore all other edges and just play this pairing strategy and you will win as maker. Now, maybe we can get this one away. Now, it's a bit more tricky to show that this is also necessary, but it's a simple, what is called inductive argument. So if we start, the induction goes on the level of, how many generations down you actually have a complete binary tree. So you have only a finite number if you don't have the infinite one. And we start with the easiest situation. You don't even have the first generation of a complete binary tree. So it looks like this. How does breaker win it? Well, he just removes this edge and game is over, no matter what hangs from it. And now you can realize what happens if this looks, oh, sorry, that was not on purpose. So it jumps to the end if I do that. That's not good. So if you have sort of a situation where there might be, say, 2 generations, but then here is not enough kids to have the next generation of a complete binary tree, then what will breaker do? Well, there is at most one, so this is, say, in the nth generation, there's a problem. So there is at most one kid that has n-1 generations with sort of full cherries hanging from it. This would be, in this case, the right one. So I choose to, as a breaker, I choose to remove this one. Then what is hanging from the other one has at most n-1 full cherry generations hanging from it. And by induction hypothesis, on this one, maker will lose it. So if I have only one generation, that's the induction base, I will lose it. If I have n generations, I can make sure I play it on n-1, and then there I will already win it as breaker. So that's actually a complete classification. If the tree T, no matter random or not, has a complete binary infinite tree rooted at the same root as the tree has a root, so the special vertex we're looking at, then maker wins it. If not, then breaker wins it. So now the question is for us, because now this became deterministic, but still the board is random. So the question now is, when do we have this complete binary tree in our Galton-Watson tree? And that has been done before. That's a paper called Branching Faster Than Binary Splitting, I think, by a Dutch mathematician Dekking in the 90s. Unfortunately, I reproved it and then I found it. So I was very happy how cute the result became, and then semi-happy that somebody did that before, but that's how life goes. So the thing is, we can now at least interpret also, so they did it just for the tree, but we can interpret it also from the perspective of the game. And in that perspective, we can say that the probability P for breaker to win the game when she starts the game is a solution to this equation here. So P equals G of P plus 1 minus P times G prime of P. So G prime is just the first derivative of our probability generating function. And that's actually also not so hard to prove. I will try to outline it because I don't know if you know Peter Winkler from the US. He once said in a talk, and that stuck with me, a math talk should contain both a joke and a proof, and preferably they should be the same. So his quote is now the joke, and I try to do the proof that hopefully is not a joke. So the probability P that a breaker wins it would be the probability, as the lemma sort of steps. I maybe try to go with the smaller pen here, otherwise this becomes so fat. So the probability that the root is not root of a complete binary tree. I write T2 for that. And that's the same as saying, well, if we look at the first generation, at most one kid is. So if the root has two kids that are the roots of a complete binary tree, then the root itself is the root of a complete binary infinite tree. So we can write it looking at the first generation as the probability that at most one kid is. And this we can actually sort of break up into how many kids there are. So assume we sort of condition on the number in the first generation. Let's say there are k kids. The probability for that is pk. And then we would have the probability that xk is less than 2, where xk is the number of kids that actually have a complete binary tree hanging from them. So this would be then binomial, because for every kid, there's a chance that it's hanging there or not, and they're independent. And the chance that it's hanging there is 1 minus p. Back to the lemma, p means there is no such tree hanging, and then breaker wins. So if there is such a complete binary tree hanging, that's when breaker loses, and that's 1 minus p. So that's, sorry, but that's the second parameter in my binomial. So that's how many are there? Well, k attempts, and 1 minus p is the success probability, if you wish. So we can rewrite this here as p0, because if there are no kids, then the chance there are kids having this property is 0, or the probability that they don't have it is 1. Same for p1. There it's guaranteed that this doesn't happen, but then from 2 onwards, we would have pk times, now let's see. What's the probability there is at most one kid? Either there is none, so all of them fail to have an infinite complete binary tree hanging from them, or there is one. So the first first probability in the binomial for xk equals 1. Now that doesn't look like what is underlined here, but it's just sort of collecting the terms and cleaning up. So if here was written, say, p times p1, that would be nice, because then this first part would be just the probability generating function. So that would be g of p, because that's p0 plus p1 times p plus p2 times p squared plus p3 times p to the third, and so on and so on. But now I cheated a little. So I still have here plus 1 minus p, p1. Now I sort of used up this term, and this part of the sum, or rather this part of the sum. So what is left is the sum from 2 to infinity, pk, and now we have the second part here, times k times 1 minus p times p to the k minus 1. But that's kind of cute, because what is standing here, that's just the summand here in front with the 1, because then it would be p1 times 1 minus p times p to the 0. That's exactly what's written here. So the first part is g of p, and the second part is actually, if you look at it hard enough, that's the g of p. That's the derivative if we move out this one in front. So that's plus 1 minus p g prime of p. Because if you derive what is called pk times p to the k, you get a k down and k minus 1 here. So that's exactly what is written up here. Okay, I hope I sort of shed a little bit light on it and didn't confuse some people with this. Not the cutest sort of way of writing it up, but it's anyway, I think, a very nice short argument. And now you can do the same, actually, the same calculation for p bar. P bar would be the probability that no kid, so no kid of the root is the root of a T2. Because if there was such a kid, then maker, who is starting now, could just connect it to the root, and then we're playing on a complete binary tree, and their maker wins it. If there's no such kid, well, then breaker wins it in the same way as the lemma says. And you actually here find out that this is even nicer. This is just g of p. In the article that is already on the archive, there's actually a small theorem about that, that in many situations you will have this. This is a more general thing, that P bar, so the probability when maker starts, is obviously bigger than the probability when breaker starts, because in this sense, sort of the game is monotone in the graph. If I add edges and vertices, that just helps maker. Also, if maker starts, that just helps maker. So P bar is bigger or equal P, and it's exactly G of P in many situations. So this is not a coincidence here. There's also I found one situation where it's actually not equal, but strictly smaller. So I hope I will get to that maybe later. Okay, so this was the setting where we reveal the whole tree at the beginning. It's slightly boring from the probabilistic perspective, but it's kind of nice that it has this link to combinatorics in the sense that you just have to try to find the complete binary tree. So what I want to drag you through next, this is some fairly standard offspring distributions that you might want to be interested to look at. One is you choose the number of kids per node to be geometric. And as we all know, there are two different geometric distributions, the one that counts the number of attempts until we succeed with something, and the other one that counts the number of failures until we succeed with something. The first one is the geometric on n, and the other one the geometric on n0. And then you can just sort of plug in the probability generating function, solve this equation here. You have to derive it, obviously, also. Solve this equation, find the unique root in 0, 1, and this will give you P. Here it's this one. And for the n0, it's that one. You can also calculate P bar. It looks like this, if you write it up in the neatest way, so to say. Why did I choose exactly this example? Because people that have heard about this extinction probability Q that we talked about earlier, they know also the criterion for that. So if the expected number of kids is bigger than 1, sometimes it's called the Malthusian parameter. If this is bigger than 1, it's supercritical. If it's less than 1, then it's, or less than or equal 1, then it's subcritical, with a small exception if everybody has exactly 1 kid. So this degenerate case, then it would be infinite tree, but not really a tree, only a line. So if we exclude that one, then the sort of expected number of kids is the interesting parameter, and the threshold is exactly at 1. Now, if you look at this one here, there are two things to notice. First of all, this phase transition from maker can win it and maker cannot win it is actually a discontinuous one. So P is the probability that breaker wins it, and this increases with S, obviously, because the bigger the S, the stochastically smaller the geometric distribution, the fewer kids, and that's good for breaker. So this increases, but then it jumps. And where it's only red, actually all the red and the blue are the same. So it jumps here from a value 2/3 to 1. It's discontinuous. It's maybe not super surprising because what we're looking for, this T2 in our tree, is a global property. And that's why it's actually discontinuous. If we do the same for the geometric on n0, it does the same. The values are a little bit different. And it does that sort of the critical value where we have this phase transition is 1/5. So why am I pointing that out? Because the expected value here is 4, and the expected value here is also 4. So you might get the crazy idea, let's call it, that here now, if this happens or not, this depends again on the expected number of kids, but not the threshold is as at 1, but at 4. But that's actually not the case. So just not to confuse you, the Q is the extinction probability. If we count the number of attempts, we always have at least one attempt, so the tree cannot die out. That's why Q is constant 0 here. Here, we actually could have childless nodes, so the tree can die out, and the probability for that is growing like this. Why is it not always 4? Well, if you do it for Poisson, and then you have an intensity parameter lambda, and there is also phase transition in the, again, in the extinction, it's at 1 because lambda is also the expectation. So as I said before, if we have an expectation bigger than 1, we're supercritical. Now, actually, here are also two things to remark. Number one, this critical parameter is the same for no matter who starts the game. Again, you might be not surprised by that, or you might. It's a local thing who starts. It's a global thing what we're looking for. So it's not so surprising that this critical value where maker has a chance to win it is actually the same for both. and this is roughly 3.3509. So it's not 4. So there's no such global constant like in the extinction. It's actually different for different distributions. It's just the two geometric that happen to have the same. So I hope you understand this sort of kind of picture I try to draw here in the different cases, because they will come in the other regimes as well. So if you don't appreciate them, you might not appreciate them further on. If you have a question, please stop me. No? Okay, so those are cool. Those are just giving us the probability that that breaker wins it, depending on the parameter lambda of the offspring distribution, in this case, Poisson. Okay, let's look at this other situation that we already sort of sketched, or I tried to sketch on the question of Amitai. When we have no other information than the internal and external vertices, then basically all the potential nodes that we can connect or disconnect as maker or breaker have the same property. They are the same. We just count the number of them. And now the interesting part is, if you have heard about the connection between Galton-Watson trees and random walks, this is not so surprising. So let me point out this connection before, if you haven't heard it. Instead of giving you the whole tree and looking at it, is it infinite or not? You can basically explore the Galton-Watson tree sort of node by node and try to find out, do I get stuck and it ends, or does this continue forever? How do you do that? Well, you count the number of nodes that you have seen as kids, but not explored yet. So you go node by node, some kind of depth first search, let's say, and it will be a random walk, because with every node that you look at, you will get a random number of kids, psi, and you will have to delete one node, the one that you looked at. So it's a random walk with the potential further nodes having a property to be a IID random walk on Z, with the increments being psi minus 1. Now, why is it here psi minus 2? Well, we have two players. What does breaker do? He kills one of them. What does maker do? The same as I just described. He will connect the next node and then get a psi number of new nodes. This is random. But so in a move of maker, you will have psi new ones, minus 1, the one we looked at. In the breaker move, minus 1, because he just kills it. So in total, it's psi minus 2 for sort of a pair of moves. One move of maker, one move of breaker gives you sort of a new addition to your list of nodes that are external, those gray ones in the picture. And this increment size is psi minus 2. Is that okay? So if we explore the tree as it is, it would be psi minus 1. If we play this game, it's psi minus 2. And here's actually where the problem starts. Because if you have an offspring distribution, it's obviously concentrated on n0. We cannot have 2.5 kids, and we cannot have negative number of kids. So it's a integer, like positive integer, or not negative integer valued random variable, this psi. And if you have psi minus 1, it's what they call a left continuous random walk, because it's sort of the increments are integer valued and the lowest value is minus 1. And they are very easy to describe and fairly easy to analyze. Now here we have not quite a left continuous one, because you can actually jump. You can sort of, on the way down, you can jump over one value. If you happen to have a childless kid, you will go down by 2. So these are not as easy to treat. And that's why we actually have here this extra condition that we have no childless nodes. Because if psi is bounded from below by 1, so if p0 is 0, then we're back in the situation that this is actually a left continuous random walk where things are fairly easy. And if you do sort of a little bit of tweaking in the way I presented in the other setting, you will find out here that the P, the probability of breaker winning this game, so if no other information is given than just the external nodes, it is a random walk like this, and you are now looking for the probability that this random walk ever hits 0, precisely as you do when you try to argue, is the tree finite or infinite in the standard situation. Then you have a random walk where it's psi minus 1 as an increment, and you are interested in the question, is this ever hitting 0? If we start at 1, then the tree dies out. If it never hits 0, if it has a positive drift and stays away from 0, then the tree is infinite. So in the same way here, just the increments are psi minus 2. And sort of making sure that we're still in the setting of left continuous walks, then you can do it. And again, you see here, this property that P bar is just G of P. So we plug the probability of winning when breaker starts into the probability generating function, gives us the probability of breaker winning when maker starts. I don't want to give you the full proof here because it's a little bit more work, but no, there's nothing spectacular happening, I can promise you. It's just Markov property and conditioning. Look at the paper if you're interested. So if we look again at the geometric as we did before, then we get this as a survival probability of our. So now you might have noticed here's just one of the two geometrics because the other one doesn't have this property. So this one we cannot treat with this theorem. If I have time, I will get back to this problem. But instead, the geometric where we count the number of attempts, this has the property that 0 is not a possible value. So we can apply the theorem and we get this as a value for the probability of breaker to win it. And since this is g of p and g of p is p squared, it's not surprising that this is just the same value squared. If we, for example, look at any offspring distribution that only takes the values 1, 2, 3 with probabilities p1, p2, p3, then we actually get, we get a symmetric random walk. A simple random walk, not necessarily symmetric. If p2 is not 0, it has some lazy parameter as well, but these are super well understood. You know, if p1 is bigger than p3, it will definitely visit 0 because it has a drift downwards. If it's a symmetric one, then it will also visit 0 infinitely often because it's recurrent. So then we also have breaker wins for sure. But if p1 is actually smaller than p3, then it has a drift upwards, and there's a positive probability that the walk never hits 0. And that's exactly this 1 minus this probability, so to say. And then again, this value squared would be the probability of breaker winning when maker starts. There's in this article by Decking, there's another offspring distribution that they looked at. They call it one or many. So offspring distribution that's concentrated on two values, 1 and some other number n that is bigger than 1. And for this, we can actually do it analytically because this one is fairly easy to solve as long as G is not complicated. And if you only have two values, G is not too complicated. So if you take, for example, n equals 4 here, so you have an offspring distribution that is either 1 or 4 with probability P1 and P4. So then you would get here P4. I should have written maybe P4 to be more specific. You get these two probabilities for breaker winning it when he or she starts and when the other one starts. And here the critical sort of the phase transition happens at 1/3, but pay attention to that now that this phase transition is a continuous one. So the probability of breaker winning goes down from 1, but continuously, there's no jump. That's different to the setting before. But again, if you think of the problem long enough, you realize that now we're looking at something local. So the question is this random walk ever hitting 0 or not? This is sort of a property that is explored locally in the tree. This is why this is a different form of phase transition here. Not as before, where we're looking at the global property of the tree. All right, so this was the second setting. I don't think I forgot anything here. I wanted to talk about, yeah, exactly. I want to talk about this problem that obviously if you can show something like this, but you have to restrict to P0 being equal to 0, that's a bit disappointing. So what you can do in case P0 is greater than 0, so you can have childless nodes, is that you sort of split the steps that are xi minus 2 in 2. So as long as you can write xi, right? If you can write xi as x1 plus x2. So if you ever heard infinite divisibility, that's way less because you just have to divide it in 2 that are IID. So if I can just write my offspring distribution as the sum of 2 integer valued random variables, then I can write xi minus 2 as x1 minus 1 and x2 minus 1. And those two summons here, they will be bounded below by minus 1. So if I can do that, then I'm back in the setting where I can look at a left continuous random walk. It will get more tricky to analyze the probability that the game actually ends with a win of breaker, because now what is interesting is if this random walk ever hits 0 or something negative on an even time mark, because it could go into 0 and then out of 0 in the intermediate step that's not relevant for the game. So here you can do something. And if you think that this property is fairly special and doesn't apply to many things, well, I can write down to what it applies. Well, for example, this one you can divide in two, because in general you can do it with a negative binomial. You can do it for Poisson. You can do it for binomial as long as there is an even number of attempts. Unfortunately, not for an odd number of attempts. So if you have a binomial with 17 attempts, this one you cannot deal in this way. But most standard distributions that you would use as an offspring distribution actually have this property that you can split them in two. So that's a whole section in the paper about how to use this sort of special property of most of the standard discrete distributions, that you can split them in two to save the situation here. But I don't want to go into that for time reasons. So let me go now into the last setting. That's maybe the most interesting one, because those two extreme where you don't tell anything or you tell everything, they're very extreme. So what if I tell you for every node that you can see, I can tell you the number of offspring it has, but what will be interesting, as we talked about, is this number infinite or not? Because if it's a finite tree hanging from it, that doesn't help Maker, and Breaker would also not do anything about it, because it will not help Breaker to win the game, Maker to win the game. So it can just, be unplayed. But if there is an infinite tree hanging from it, well, then Maker would want to connect to this node and Breaker would want to cut it off. So now, again, we look at sort of a random walk as before, but now just at the nodes that are root to an infinite subtree. So that's the good and the bad news at the same time. What is the good news? If you think about it, every node that has an infinite subtree hanging from it has at least one kid that has this property. So by default, we always have at least one kid with this search for property. So what was an issue before, that we can have no kids hanging from it, this cannot happen, because now we focus on the nodes that have infinite subtrees hanging from it. But every node that has such a tree hanging from it has at least one kid that has such a tree hanging from it, right? Because if you have only kids with finite offspring, you have only finite offspring. So that's the good news. We'll not run into this problem. The bad news is, well, you have to do the math, right? Because before, the offspring distribution gave you the number of kids in either case. Now we condition on it that there is infinite a tree hanging from it. That will change the probability of having k kids, obviously, because it will sort of, tilt the offspring distribution stochastically upwards. So to say, if I tell you that there's an infinite tree hanging from it, well, then more kids is more likely. But that's not too hard. That's just a conditioning that you have to do and sort of do the nitty-gritty algebra, and then you end up with this offspring distribution that I call now psi prime, so to say. This one actually doesn't belong there. I don't know how it made it there. Shouldn't be there. So we have now offspring distribution or increment distribution in our random walk that we look at of the playable nodes. That is again psi prime minus 2. But now it's not psi here, but psi prime, and psi prime has this distribution, where obviously psi comes in, but in this way. All right, so if you do the same trick, then you just try to analyze when is this random walk hitting 0, and when it takes off to plus infinity without ever doing that, hitting 0. Then you will find the probability of Breaker winning it, namely when this random walk hits 0, and the probability of Maker winning it when it doesn't. And now the probability generating function comes in here, but not with the derivative as in the first setting, and also not with a very simple form as before, but now also Q enters the picture here. So the probability of dying out is here all over the place. So if you want to find P, the probability for Breaker to win it, you would have to solve this equation where Q is the extinction probability, G is the probability generating function, and X is your variable, and P is the solution to that. And again, P bar would be, if you find P, just plug it back into the probability generating function and you find P bar. Okay, sounds tricky, but we can do anyway some simple example. So if we now look at the offspring distribution that is concentrated on 0, 1, 2, 3, so as before, but now we have no issues allowing also 0, then you can actually do it explicitly and you find out it's exactly that. So here, actually, the derivative comes in. So P would be G prime of Q divided by the probability of having 3 kids times 1, so the survival probability, 1 minus Q squared. And then this, the square of the whole thing would be the probability if maker starts for breaker to win it. How does that look if I take, so this is a special case of this one. If I take a binomial with 3 attempts, it's concentrated on 0, 1, 2, 3, obviously. So if we do that, then we can first calculate the probability for the tree to die out. This is this one. And then the probability of breaker winning the game when it starts, and then P bar once we have P. And we get those 3 curves like this. Similar picture as before. The phase transitions are the same for P and P bar, and they're both continuous. This is more sort of very similar to so this third setting where you tell sort of which nodes have an infinite offspring, which doesn't. That's more similar to the second setting where you don't tell anything at all in the qualitative aspect, how the phase transition looks, than when you tell all of it. So here I tried for the Poisson distribution actually to paint all 3 curves. So if you have the situation where you don't tell anything more than the external nodes, this phase transition is at 2. And actually, both for the situation where you don't tell anything and where you tell which trees have an infinite offspring, which subtrees are infinite, which subtrees are not for each vertex once you see the vertex. So that's even the same for those 2. And you can already see that more information is actually helping breaker. So this is no information. This is I tell you where the infinite subtrees are, and this is I tell you everything. And the more we tell, the better for breaker. This is also not so surprising because sort of a move of breaker has a more global effect because you cut off a whole subtree than one of maker because it adds just 1 node. So the more information I tell you, the more it helps the player that has the global sort of effect. So that was this picture, but I wanted to point out a bit more. So as I said, one technical issue here is that if you have P0 bigger than 0 in the regime where you tell not more than just which external nodes are we looking at, is that you deal with the random walk that is not left continuous. And that sort of gets very busy with the technical analysis. But as far as I could do it, it's in the paper in case you're interested. There are many possible information regimes that has not been looked at. For example, you could tell not only, so if I tell you where the external node sits, that's the regime where I tell you nothing more than that. But I could tell you, instead of saying how many, sort of how big is the tree hanging from it, so a global thing, I just tell you how many kids everyone has. So maybe it's maybe not so cool, but I do a quick move back to this tree. So with every node that is visible, I will tell you this one has 4 kids hanging from it. This one has 2 kids hanging from it. Then we're in a new situation where the different nodes that are interesting for play are not the same, because this one has 2 kids is not as interesting for both players as the one that has 4 kids hanging from it. So they would target the one with the most kids first. And then the situation gets pretty tricky because sort of depending how many kids are adjacent to each node, they have a different role. They're sort of have a different value for the players. So then it becomes not as easy to analyze how the game would go on. Or for example, you could tell not the whole tree hanging from it, but just say 3 generations down. So I tell you not only how many kids and how many grandkids, but also the structure of the tree, those 2 generations down, for example. There are many things that sort of could be doable, but most of them I tried to look at, they turn out to be really tricky. There are some low-hanging fruits anyway. For example, if we go to the biased game that I shortly talked about, so say one breaker gets to kill 1 edge and then maker, no, sorry, this is actually the other way around when we say maker is the second player, so breaker starts, that you sort of look at the biased game, and if it is that breaker can kill D edges for every edge that maker adds to the fixated edges, then you would now not need a complete binary tree, but you would need a complete d-ary tree. the same argument applies. So there's definitely things that are fairly easy. If you turn it around and you allow maker to fixate the edges before breaker gets to kill one edge, then it's a bit different. Then you would sort of look at sort of a complete binary tree that has sort of minors instead of edges. So there's sort of in between two of the nodes of this complete binary tree, there can be other nodes, but the length is not larger than D, because then breaker has a chance to cut it off. So it's not too hard actually to deal with this biased game, at least in a situation where you don't, where you tell everything. That's should be fairly easy doable. One thing I want to point out is also that this information symmetry that we assumed, so both maker and breaker gets the same information. This is sort of, I think, something that you cannot get rid of without losing basically all your tools, because think about the situation where maker gets to know, I don't know, for example, how many kids every node has, and breaker does not get to know that information. Then actually breaker can learn from maker's moves which ones have which property. So say, maybe with the kids it's not entirely obvious, but if maker gets to see the trees that are hanging from the external nodes 3 generations down, and maker gets no information, well, the corner where maker is playing, this is obviously the one where there's a lot of extra kids hanging from it. So basically maker reveals some information by playing there. It gets highly non-trivial, how they learn the strategy from how the other players is moving. And then one thing that I also haven't talked about and sort of tried to divert your attention from it. No one ever asked. I had a talk before about this sort of in real life, not online. And there the first question was, well, do you tell the players the distribution of Xi or not? Actually, in these situations we looked at here, it doesn't make any difference. I can tell them, I cannot tell them. But there are situations where it does make a difference. Think about the situation when maker and breaker, they get to know if the number of kids is odd or even. This information is completely different if I also know that Xi is concentrated on values 1 and 1 million, because then I know even means 1 million kids and odd means 1 kid. If they don't know that, well, then odd and even doesn't give much information, because they would still want to go for the one with most kids. So if it's 17 or 18, well, that's reversed to 17 or 16. So the information odd or even is not really helpful. But if you know the distribution of the number of kids and it has this very weird distribution, that could be very, very valuable information. So there it comes actually even in a difference in knowing Xi or not. And then the last question is maybe interesting for the people that are normally looking at the speed of conversions and stuff. So if maker wins, the game goes on forever. That's not so interesting. But if breaker wins it, how many nodes can actually maker connect to the root before it's game over? Because here it gets also a little bit more tricky, because you would have to look also at the finite parts, right? As in this connectivity scenario, it doesn't make any sense for the players to play in a finite subgraph, or where it's only a finite subtree hanging from it. But in the situation where you try to connect as many vertices as you can before the game is game over for maker, then even those ones could be interesting. So there it gets more tricky to analyze. Those are the 2 papers. So this talk was based on the first one here. You find it on the archive. Just Google for my new name, so to say, or rather archive for my new name. And the other one is what was needed to actually deal with the situation where we have to split the increments in 2. That turned out to be interesting enough to write a short paper about it. And now, since I'm exactly on the hour, I want to wrap up with giving you a short history of related stuff. So obviously this branching process business, you will find in this standard reference from Atreya and Ney from the 70s. There's a lot of things more than what I presented here about the Galton-Watson trees and BNMA branching processes, however you want to call that one. Then this paper from the early 90s that is sort of more or less solving the situation where you have the full information, like the game is played on the tree, but that is random, but it's known from the start how it looks like. Then there is a paper by Holroyd and Martin that looked at a slightly different one. You played on a Galton-Watson trees. That's why it's very similar to this here, but the game is different because there you move a token and you basically, depending, they have 3 different variants. Either once you move it to a leaf, you lose or you win. That's already two different games. Or one player tries to win by moving it to a leaf, and the other one tries to avoid that. So there are two different games to look at. So similar here, the random board, not similar, the games, the rules of the game. Then what is very close to what we looked at here is actually those two papers by Day and Vargas from Umeå. I think Nick Day is there not anymore, but Victor still is. And they basically look at the same thing that we looked at here, just not played on a tree. They play on a grid and try to cross grids or try to prevent that. And they do it also. This was, for example, one thing that they looked at in set D or in set 2, as I tried to present in this short intro, can actually make sure that the origin is not cut off in a finite component. And then what is in the whole perspective closest to the work here is actually sort of a continuation on this second paper by Day and Vargas by Dvorak, Mond, and Sousa. That's also on the archive, very recent. They look at this on a percolation sort of subgraph of set 2. So they do the classical bond percolation. Every edge gets removed with a probability 1 minus p, say, and then you play it on what is left. And it's actually interesting what they found, namely this pairing strategy that we said that guarantees maker to win the game on set 2. That does not apply to the percolation, no matter if it's obviously if it's subcritical, no chance for maker winning it. Although they allow actually maker to choose the origin, because now not all the nodes are the same, right? So, but that doesn't help if there are only finite components. But even if there are infinite components and maker can place the vertex wherever they want in the infinite component, actually, no matter how p is, no matter how close to 1 it is, breaker will win it. So as soon as you go to a percolation subgraph of set 2, it's actually a breaker win. That's in this paper. So now I'm anyway 2 minutes over, but that was all I wanted to tell you about this topic. I hope you have understood most of it or parts of it and appreciate that parts and not appreciate the others. If you have further questions, please feel free to ask them.
Thank you, Timo. Let's maybe. Any questions?
Yeah.
Amitai.
I have a couple of questions. So far, as I understood, maybe I missed something. I mean, I have very loose questions over here because I had more, but you already covered them.
You sound like an opponent in a defense, but that's okay.
I am the breaker here.
Okay.
So my question is the following. You define this game always to be played on an infinite graph, right? Because you want to just consider the infinite component or finite component. But perhaps you can define the same game and trying to connect 2 points, right? For instance.
Right.
And perhaps then you can define the game on a locally tree network, for instance, an Erdos-Renyi. So perhaps you can, is there a way to translate what you have found in trees to those kind of graphs?
Right. So the game that you were hinting at is actually at the origin of this. It's called the Shannon switching game. So where you have two nodes and you try to, or even 2 sets of nodes and you try to keep them connected. That was sort of on a finite graph. That was sort of the first thing anybody ever looked at in this perspective. It was not even called maker breaker back then. It was called Shannon switching game because, yeah. So this is sort of the oldest thing of this kind. And yes, there has been done a lot. You will, if you search for this paper here, you will find most of it in the related work section. On random graphs like GNP, things like this. How can maker make sure that 2 vertices stay connected or 2 sets of vertices stay connected? Can maker actually secure a perfect matching or not? Can maker secure a Hamiltonian cycle or not? Spanning tree, all those things are already looked at. So just to be clear, I just want to be exact here. That's, I think, a professional deformation of any mathematician. When you say I'm looking at infinite trees, that's actually a lie. I'm looking at a random tree, and it can well be finite, but then it's already a maker's loss. So the interesting part is only when the tree is infinite, as you said. But in principle, it could happen, right?
Yeah, but then you just declare the game over from the beginning.
Right. Exactly. Well, in the case they don't get to see the tree, they will find out soon enough that it's a no way Jose situation for maker. If they play one by one and then find out it was a finite tree, game over.
Yeah, of course. And if you have no information, then you cannot exit at the beginning. You just have to
right. You will find out at some point.
Okay, so my other question is a much looser question, because when you started describing this model, I kind of just drew a very thin connection to another problem, which is the Angel Devil game. Have you heard of it?
No. Can you explain it short, or is it difficult?
Yeah, it's basically is that you have two players in a grid, right? An angel that is just jumping in several directions, and a devil that has just is removing sides on the grid and starting and trying to keep it on a finite component. So it's I think it's okay. So then you, by not knowing this game, you already answered my question that you haven't heard of it.
No, but I mean, I see the connection here, and honestly, this paper by Holroyd and Martin goes in this direction where one tries to reach a leaf and the other one tries to avoid that. That's sort of in this direction that you have one, they call it escape or stopper game, I think. And one player tries to stop the other one from escaping, and the other one tries to escape the situation before it gets sort of caught in a leaf. That would be the same, just not on a tree.
Yeah. Okay. No, just wanted to see if
But I mean, they look at
there
the
was like
directive,
a coupling or whatever.
right? They look at there's a lot of things that you can do with coupling. As I shortly pointed out, there is this monotonicity in the graph, right? If you add more edges or more nodes, that helps maker. So if you can, for example, this is one way to deal with those binomials that have an odd number of attempts. You cannot split it in two, but compare it with one more attempt and one less attempt. And then one is helping maker and the other one is helping breaker. So if I can calculate the probability for breaker winning on a binomial 18.5, and I can calculate it for binomial 16.5, the one for binomial 17.5 must be in between the two.
Yeah.
So with the couplings, you can do a lot, but I cannot immediately see a coupling here between the game you described, this Angel Devil, and this game, but they're kind of related. It looks from the type of game, yes.
Okay. No, that's it. And also, if you have yourself check these information asymmetry cases.
No, because I just tried to sort of in this situation where things are fairly easy. So say maybe one sees the full tree and the other one gets no information, stuff like this. So this seems like the first attempt to do something when the sets of information are still pretty trivial, but not both. Because the biggest problem is if, say, breaker gets to see nothing and maker gets to see the whole tree, the problem will be that you can sort of self-similar way as the tree has, right? As soon as you go to a subtree, it's basically playing the game on the same thing as from the start, but just now on a subtree of it. This will not hold anymore, because by going to a subtree, the breaker that didn't know nothing learns actually something about the tree. Whenever you go to the next generation, the game is a new game. It's not the same game. And that will basically blow up all nice arguments you can have in this board.
Okay, I can see that.
So that's highly non-trivial. It's interesting to think about it, but it's not obvious what you have to do to get into a situation where you can prove something.
Okay. Okay, that's it. Thank you.
Cool. Thank you for your questions.
You want me to try someone else? I'm stupid. Just what was the original motivation of this maker breaker game?
So I heard a talk by Victor Fargas in Umeå about this on Z2, and they actually had a very not so cute proof that breaker has no chance winning it in this 1-1 situation on Z2. So I told him about, well, why not have this pairing strategy and he found that kind of cute. And, well, basically here it's enough tree binary when you always can choose one of two edges to keep, and that's sort of keeping the whole thing together. So then my idea, why not looking at a tree? But then things are fairly boring if everything is deterministic. So I thought, why not playing on a random board? And that's how it started. And then I sort of got extra motivated when I found that people already did something in this direction. They didn't call it a game, they just sort of analyzed Watson trees. So that sort of was the starting point of it. But obviously that's a big step from being able to analyze the game on a tree and to be able to analyze the game as circles, because then now here every edge is crucial, right? If you cut it, whatever is on the other side is gone. If you have sort of circles, maker can accept the edges of the. If you kill a second, it's crucial. So that makes completely different sort of maker a 3-edge circle.
So fractional versions that they with a certain breaker can, and then he turns, or is there always is one always one turn only? Is that enough?
I looked only at this 1-1 game. First, sort of general would be to look at the biased version of it, because I mean, in this situation, most of the times actually breaker has a big advantage, because as I said, the effect of a move of breaker is way bigger than the move of maker. So if you say maker to fixate 5-edge, breaker is allowed to cut 1, that could be a more interesting situation. But what you are working for is actually the last paper. They did sort of look at the version where every edge is sort of hated maker breaker with certain probability. So it's actually every edge, you flip a coin, who gets it?
Okay.
And that's obviously changing the whole game, because yeah, magic in some sense, but yeah, to is that's the edge that the other one. So it's it's different. Like it becomes different that you would have to use other tools to have. But definitely, yes.
Yeah, thank you. That one to ask it, Aurelio, Daniel.
No, I had similar questions as Amitai, so they were answered already.
Now you sound like somebody from the committee after the opponent
Actually,
asked all the questions. Yeah.
yes, you're right. But it was true.
Do I get a degree at the end of this? No.
Maybe.
Okay, well, if not, then let's thank Timo.
Thank you for having me.